So one of the first problems you went into in calculus is called the tangent line problem, all right? Why is this a problem? Well, in stagnant world, if I said, what is the slope? You would immediately think y equals mx plus b, and the slope is m, and we are done because the slope is constant in a pre-calculus world. But in a calculus world, they want the slope of something like this parabola. Well, now we have a problem because if you'll notice, if I'm here, well, the slope of that parabola looks like this, very sharp positive. But what happens if I want the slope over here? Well, that's going to be a very sharp negative. And what happens if I want the slope down here? Well, that's a positive, but not as sharp as a positive. So we are now no longer in a stagnant world of slope. We are in a changing world of slope. And so we have to look at how it changes. Now, what I want you to see down here is what's called the instantaneous rate of change. Instantaneous rate of change represents the slope at one exact point. You can only have one answer, instantaneous rate of change. And this is f of x minus f of x over h. Now, I will tell you, they are doing it over a period of time. And so if you look at the figure that is right above this, all right, so what they're going to do is f of x just represents my y value at x, right? F of x means y. We all know that. And so what they're basically doing is they're saying, well, here is x. So x is right here. Over here is x plus some number. We'll just call that number h, okay? All right. So my y value here is going to be f of x. My y value here is going to be f of x plus h, however far I moved. I'm at a new x, all right? They've taken my y value at my new x, subtracted my y value of my original x. So they've taken my second y value and they have subtracted my first y value. And they have it over h. Well, what is h? Well, h is the difference between my first and second x, right? If I take x plus h minus x, I get h. So basically, they've taken my second x, and they subtracted my first x. That looks vaguely familiar. What does that look like? Looks like slope, all right? So when they ask for this, they're basically asking for the slope formula. But in a world that changes, we are looking for the limit in a slope formula. So we are looking for, well, what happens then? So if I want it, basically what they do is they want it at a specific point. So they've taken two different points. They've taken these 2 points. And what they're going to do is they're going to get ever close to the actual point. So they want the distance between the two x's to get smaller and smaller and smaller and smaller till it is the same, which means the distance between the two would be 0. So we're looking at what happens as the limit approaches 0 of your slope formula, meaning instead of having x's that are really far apart, you're trying to get that line as close to actual slope that you can, where it's you're looking for basically a tangent line where it barely touches it once. It only touches it once. So they start with a secant line, touches it twice, and they move those points ever close to each other until you're at the exact point that you want that slope. And that's why the limit is 0, because they want those 2 points to actually come all the way together, and when you subtract them, you actually are 0. There's no difference between the 2 points. You're just at a tangent line, all right? So they've taken it and they've used a limit formula. All right, and this is all assuming that the limit exists. If the limit does not exist, we have another issue and we can't use this, all right? So let's look at the first example. Find the slope of the line tangent to the graph y equals x squared at the point 1, 1. All right, at the point 1, 1. Now, we are going to put in our point. We do not have an h at this point, and we are going to see what happens. We're going to use our formula. So we're going to say the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h, which we do not know. What is my function? My function is x squared. So what do I do to find the y value given x? I just plug it in, right? My x here is 1 plus h. So f of 1 plus h is going to be, this is x squared. We have to plug it in, right? Is going to be 1 plus h squared, right? Then we plug in our 1 minus 1 squared. That's my x value, right? Over my h. So far, so good. What do I do with this guy? Well, I FOIL him, right? 1 plus h times 1 plus h. So I have 1 plus 2h plus h squared. Everybody agree with that? Minus 1? Yes? Yes. All over h. Can I simplify my numerator? Yes, right? I basically have h squared, I'm going to put it in order, plus 2h all over h. Can I simplify it anymore? I can take an h out of everything, right? So I take an h out here, h out here, h out here. I get h plus 2, all right? Now, where I had a problem with my limit here, right? I can't just plug it in, can I? No, why? I'd have a 0 in the denominator. But when I simplified it, I no longer have a problem. What is my limit? 2. What did I answer? That is the slope of the tangent line to that graph at the point 1, 1. Now, it will be different if I asked for the point negative 1, 1. It would be a different slope, all right? But at this point right here, the slope of the line that touches that graph exactly at that point is the slope 2. It means the slope of that line is 2. It goes up 2 over 1, up 2 over 1. The slope of the tangent line is 2 at that point. And that is only at that point. If I pick another point on that graph, the slope will change. All right? Because it is continually changing. It is a parabola. It is continually changing. So if I pick a different point, if I picked this point over here, the tangent line at that point is obviously going to have a different slope. It's going to have a negative slope over there, right? So it is point specific. The slope is point specific. It depends on where on that graph you are as to what the slope is going to be. So my x here is 3. That's the value I'm going to use here. So I want to do f of x plus h minus f of x all over h. And I want to do the limit as h approaches 0.
So it's always going to be h approaching 0?
Correct. This is the formula for it. All right, so when I plug it in using these, it's f of 3 plus h minus f of 3 all over h. So what does that mean? Well, that means I'm going to plug in 3 plus h into my function, and I'm going to plug in 3 into my function. My function is x squared, so this is what I'm putting in for x right there. I'm putting that whole thing in for x. So this guy right here is going to be 3 plus h. That's what I'm plugging in for x in that function squared.
So why can 3 plus...
This is going to be 3 squared. All right, so if I had the same problem and I was like, I want you to find the slope at 1, 1, and at 2, 5, and at 4, 7, and you'd have to do this over and over and over and over. You're like, can you make me stop, please? So what you can do is you can find one at any point. So what you do is you do the process without plugging in a number. Just leave variables in there, okay? And then it will work for any point on the graph. And then all you have to do is plug in the x value, and you're good to go. All right, so let's look at this one. We want f of x plus h minus f of x all over h. It is the limit as h approaches 0. All right? So now we're not going to have a number for x we're just going to leave the variable there. All right? So my my function is y equals 4 over x. So I'm going to take x plus h and plug it in here, right? I'm going to take x and obviously plug it in there. It's the same thing. So x plus h plugged in, well, that's 4 over x plus h, right? That's all I did. I just plugged in an x plus h minus 4 over x. Yes? All over h. All right? So far, so good? Okay. All right. And this is as h approaches 0, right? Okay. Now, what do we do? Well, we want to get common denominators. We want to simplify it just a little bit. So I'm going to get a common denominator, and then basically I'm going to keep change flip, right? I have h, and I'm going to get 1 over h, etc. All right? So common denominator here is just x plus h. Everybody agree with that? So I multiply this guy by x. I multiply this guy by x plus h. Yes? So I get 4x minus, distribute that negative, please. 4x minus 4h, right? Just common denominator, all over x plus h, all over h. Now at the top, you should see something that stands out. What can I simplify up there? Yeah, these guys cancel. So I am at this point, I've got my numerator of negative 4h over x plus h. Keep, change to multiplication, flip. What does this flip to? 1 over h, right? So far, so good. All right, what can I do here? I'm multiplying fractions. Yeah, I have h's that cancel out, h's. And then I'm just multiplying across. Negative 4 over x plus h. But I am doing limit as h approaches 0. Can I plug in a 0 without causing a problem? No. Yes, I can. All right, if I plug in a 0, no problem. What's my answer? Negative 4 over x squared. This now gives me a new function. All right, gives me a new function. Meaning now I can say, what is the tangent of the slope at the point x equals 1? I can plug in a 1. It's going to be negative 4. Well, what is it when I'm at 2? Oh, well, it's negative 4 over 2 squared. It's negative 1, right? So now I can choose any point on my graph and give you the slope of the tangent line at that specific point, okay? Instead of doing it for this point, and then for this point, and then for this point, and then for this point. Make sense? So let's review homework. Find the slopes of the tangent line to the graph at each of the given points. So they want us to find the slopes of these graphs at these specific points. And then they want to find for the second one, find the equation for the slope of the graph at any point. So you actually could have done any point here if you wanted to and just plugged in your 1 and 5. Or you could have done the 1 and 5 individually. Whatever you want to do. So we're going to use our f of x plus h minus f of x over h limit, okay? So we're going to say the limit as h approaches 0 of f of x. We're just going to start with the 1 plus h minus f of 1 all over h. So we have to see what happens when we plug in a 1 plus h. Well, when we plug in a 1 plus h, we've got to plug it into every one of our x's. All right? So this first one is going to be 1 plus h squared, that's x squared, minus 5x, or 1 plus h. All right, that's my f of 1 plus h, right? Minus f of 1. Well, f of 1 is going to just be x squared minus 5 times x. And my x there is 1. All over h. All right. So far, so good. Then I'm just going to simplify this. This one I squared is 1 plus 2h plus h squared, distribute that negative 5, minus 5h. This is just going to be 1 minus 5, so this is negative 4, but it's minus a negative 4, so plus 4. All over h. All right. Then I'm going to simplify again. I have 1 minus 5 plus 4. What happens there? 1 minus 5 plus 4. It zeroes out, right? So then I have 2h, or I have h squared. We'll do h squared first. Minus 2h minus 5h is minus 3h. All over h. Right? Yes. All right. So, what can I do?
Take out an h.
Take out an h. So I have the limit as h approaches 0 of h minus 3. I no longer have a problem. So what is my limit? Negative 3. That entire, so my formula says to use my x value plus h. If I'm plugging this whole thing in, this is the x squared minus 5x. All right, this over here is the x squared minus 5x. I'm just plugging that whole thing in. And my formula, and here's the thing, you have x's, everywhere, all right? This is just your input. What is my input? My input is the 1 plus h. In the formula, it's f of x plus h minus f of x all over h, okay? Which means I'm going to input this group into whatever function they gave me for every single input value. Here I have an input value of x squared and 5x. I have to put it both places.
Okay, I was just.
All right, let's look at this one. Basically, this one is saying, hey, I don't want you to plug in a specific x. I actually want you to figure out what it would be for any value on the entire function. So we are going to literally use x plus h and not put a value in for x. We're going to just do the function itself. So we're still going to use the same formula, f of x plus h minus f of x all over h. All right? That x plus h has to go in as a group for that x squared. So this piece of it plugs the x plus h in. All right? So we have x squared, x plus h squared plus 3. That's my first part. Minus f of x is just your original function. Like y and f of x are the same thing. So when you're doing this, it's just whatever it gave you, right? Minus x squared plus 3, right? All over h. Don't forget that we are doing limit as h approaches 0, all right? So I do need to FOIL this guy. We have x squared plus 2xh plus h squared plus 3 minus x squared minus 3. Number one problem when people do this is they do not distribute the negative, by the way, all over h. Don't forget you're doing limit, all right? All right, so a couple things cancel out here. My x squareds cancel out, my 3's cancel out. And then you're left with this part over the h, so you can cancel 1h out of everything. And I have the limit as h approaches 0 of 2x plus h. If I plug in a 0 there, I get 2x. What does this mean? Well, it means if I want the slope of a tangent line anywhere on that graph, I can plug it in. If I want the slope at 0, well, the slope at 0 is going to be 0. If I want the slope at 1, it's going to be 2. If I want the slope at negative 2, my slope is going to be negative 4. It makes sense. It's a parabola, so it's going to look like this. So it looks like it should change, right? Anywhere. Whereas in problem 1, you did this whole process with plugging in a 1. Then you did the whole process with plugging in a 5, okay? So if I had done problem 1, which was x squared minus 5x, if I had done this particular problem and just found the new function. The new function for this one would be 2x minus 5, by the way. So if I plug in a 1, right, we want to know what the slope is at 1. Well, the slope at 1 would be what happens when I plug in a 1 here. Lo and behold, I get -3. They wanted the slope at 5. Well, if I want to find out the slope at 5, I plug in a 5. Gives me 5. All right, so instead of doing that whole process with each one of the numbers, you can do it without plugging in an actual number, get a new function, and now you can plug in any number you want and get any slope anywhere on the function itself. Okay? What is a derivative? All right, so derivative is the term that is used for finding the new function. All right, so when we find rate of change or the slope of the tangent line, we are finding it at a specific point. Slope of the tangent line at the point 1,5. All right, when you find the new function at any point, you are actually finding the derivative of the function. That's what it's called. All right, why do we need this? Well, one of the first things it's used for is finding the slope of the tangent line. Derivative is going to be used for a lot more things as you go on through calculus, but the first thing it's used for is finding the slope of the tangent line at any point. And so you'll notice that the formula for derivative looks vaguely familiar. It looks like what we've been doing like this whole time, right? There is a little bit of notation I want you to pay attention to. Okay, so you'll notice you have this little prime mark right here. So you have the original function is going to be your f of x or y, or it can be written like this, y. When you find the new function, this limit formula function, that gives you the slope of the tangent at any point, right? So that means it has an x value in it. You are going to write that with the notation with a little prime, whether it's f prime of x or y prime. That indicates that you are using the new function. This is not your original function. This is a new function that represents finding the slope of the tangent line, okay? And so it is called the derivative, and it is notated with that little prime mark. So you want to make sure you know how to notate it because you're going to use it going forward. So we have this concept, which obviously I brought it in right here, instantaneous rate of change, all right? When you're talking about rates of change, slope formula would have been y2 minus y1 over x2 minus x1. Instantaneous, that means we have movement going on. So we're moving along a parabola, and I want to stop at a specific point and say, what is the slope right here? That is instantaneous rate of change versus average rate of change. I'm going to give you this example. You're driving to Columbia, and you say, I drove 50 miles an hour. Okay, well, not all the way, right? Or I drove 70. Probably not from here to the interstate. You didn't, especially this morning, right? So when you're telling me I drove 65 miles an hour from here to Columbia, you are telling me the average rate of change. You took your entire miles divided by your entire hours, and you gave me an average rate of change. But what if I said, well, at mile marker 207, how fast were you driving? That's instantaneous. At that moment in time, I was driving 65 miles an hour. All right? Or at that, if I said, what about, at the Ashley Phosphate and the interstate? Okay, at that exact moment, I was going 20 miles an hour. Instantaneous rate of change. Okay, you see the difference? So instead of giving me an average, which is what you've done in the pre-calculus world, in the calculus world, you're going to be able to tell me at an exact moment what the rate of change was. It's like going along the parabola. All right, you could give me an average from one point to the other. That's just 2 points and giving me the slope of the line that goes from those 2 points. Or you could travel along the parabola, and at a split moment in time, you're going to say, right here, my rate of change is this, or my slope is this. That's the difference in the two, okay? So average is just going to be my 2 y's divided by my 2 x's, average. Instantaneous is going to use your limit formula, And all of a sudden you can give me a more specific answer to the question. All right, and so that's why instantaneous rate of change looks like this. And if you were looking at average rate of change, it would be 2y's divided by 2x as your general slope formula that you've always known. All right, so let's look at some rules for this, the power rule. I want to actually give you a couple things here. Before we get to this, I want to give you some examples and see if we can glean from it what I'm doing. So if I were to give you an original function like we did from homework, and I were to say, well, your original function is x squared minus 5x. All right, and actually I'll just use the x squared part. We'll just use the x squared part. If I were to calculate rate of change at any point without plugging in a number, your derivative here is going to be 2x. All right. If I were to do f of x equals x cubed, your derivative here is going to be 3x squared. If I were to do f of x equals x to the 5th, your derivative here would be 5x to the 4th. Do you see a pattern? That is the first rule. Power rule for derivatives. In order to find the new function that gives you your instantaneous rate of change, or that gives you the slope of the tangent line, or that gives you the first derivative, your exponent is multiplied by your function. It becomes your coefficient, okay? Your new exponent drops by 1, which is what it's telling you here. If your function looks like this, x to some power, then the derivative of that function is the power in front, and your exponent drops by 1. Exponent drops by 1. All right, so let's look at some examples. All right, the first one, x to the 9th. My derivative here is going to be what? 9x to the 8th. All right. Let's look at the next one. If I have a radical, the very first step here is to rewrite it in exponential form. All right? So before I actually take my derivative, you'll notice that I do not have my prime function notated here. I'm still in the same original function. I am going to rewrite it. How am I going to rewrite the 5th root of x to the 7th? My numerator is what? 7. My denominator is 5. Remember, you can write it in fraction form, okay? Now I can use the same rule as it applies. My derivative then, you'll notice I now have the derivative mark. My coefficient is going to be 7/5 x to the, I need to subtract 1. What is 1 in common denominator here? It's 5/5, right? So my new exponent is going to be 2/5. Now you can leave it like that, or I want you to recognize if you were to take like an ACT or something that it could be written like that, or it could be written in 5th root of x squared. Okay, but I will actually take it in the 7/5 form. I mean the 2/5 form. You don't have to rewrite it if you don't need to. I mean you can leave it in exponential form. All right, let's look at the next one. I also want to rewrite this guy. All right, in the denominator, so I am just rewriting it. I'm actually not taking the derivative right now. If it's in the denominator, how would I write that in exponential form? X to the, what puts it in the denominator? -8, correct? X to the -8 is 1/, x to the 8th, right? So now I'm going to take my derivative. My coefficient then, what's my coefficient? -8 x to the -9th. I am going down by 1. I am going down by 1. Now this guy you do want to rewrite. Don't leave a negative exponent. That's hideous. So we would say it's going to be -8 over x to the 9th. All right? -8 over x to the 9th. So try those 3. All right, constant rule. The derivative of any constant is 0. Why is this the case? Well, if I have the function y equals 5, all right, first of all, what type of line is that? Well, if I were to draw this on the coordinate plane, y equals 5 would look like this guy right here, right? It's just a horizontal line. What kind of slope do you think that thing has? Anywhere on the line, what is the slope of that? 0, right? It is flat, okay? So remember, first derivative represents the slope of the tangent line. Well, first of all, the slope of a horizontal line is always 0, so the slope of a tangent line to that is also always going to be 0. Why else is this important? Well, you can use your rules. It is 5x to the 0 power. Is that not 5? X to the 0 is just 1. So if I were to use my rule that I just had, 0 times the front of it, it doesn't really matter what happens to x because it's a 0, right? It's being multiplied by it. So anytime you have just a constant, just a number, and you are taking the derivative of a number, it is going to derive to 0, all right, because it represents a flat part of the function. Constant, let's say you have a number in front of your function before you ever start. Well, when you multiply it by that exponent, you just multiply those guys, okay? Let's say you have a polynomial where you're adding monomials. You just take the derivatives and add the derivatives, okay? So let's look at some of these examples. 5x cubed plus 4. They want me to do the derivative of this. So the derivative, I'm going to do them individually. Here, I'm going to say 3 multiplied in front. 3 times 5. What is my coefficient? 15. X to the, what's my new exponent?
14.
So it's 2. All right? Plus, I have a constant. What's the derivative of any constant? 0. So my derivative here is just going to be 15x squared. All right, that is my derivative. All right, let's look at this next one. I have this craziness going on right now. Now we will introduce product rules, but right now I'm just going to distribute that. So I'm going to distribute it first before I take the derivative. So my g of x is 2x to the 8th plus 4x to the 5th. And now I'm going to take my derivative. So my derivative of this individually, 8 times 2 becomes my coefficient. Yep. My new exponent is 7 plus 5 times 4. And my new exponent is 4. That is my derivative. Now, wouldn't that be much better than doing the limit theory here and adding x plus h to the 8th power? Oh, dear. All right, let's look at the last one. For something like this, I'm going to take each one divided by. So I am going to rewrite this first to look like this. All right, I'm going to say 5x cubed over x minus 12x over x plus 6 x to the 5 halves over x. All right, so see what I'm doing here? So I can reduce each one of these. 5x cubed over x is going to be just what? 5x squared. Minus, what happens to the second group? Just 12. Plus, this is, I subtract here, right? This is 2 over 2, right? So this is going to be 6x to the 3 halves. Now I'm going to take my derivative. Now that I have it looking like that, all right? So then my derivative here, do it individually. What's my coefficient here? 10x to the first power. What happens here? It zeroes out. Plus 3 halves times 6 is what? Which is 9. And it's going to be x to the 1 half. I will let you leave it like that, or you can write square root of x. Either one. If you're plugging something in, you might want to write it as square root of x because it makes more sense. But if you're just doing the derivative, I will take fractional exponents. The first thing is what we just talked about at the very beginning of this chapter, instantaneous velocity versus average velocity. All right? So when you study physics, hopefully you study velocity and acceleration, all right? But you have a position function. The position function, think of it as like your parabola function, your standard quadratic, all right? If I were to throw a ball in the air, it's going to be a parabola, right? I throw it up, it goes to a peak, it falls back down, all right? It creates a parabola, all right? Happens with, balls are just the best example. I think they actually do this as well here. That's my position function. So the x squared plus 3x minus 5, my quadratic, is just position. If I want to know how high in the air at any moment that ball is, then I'm going to say, well, once the ball has traveled 3 feet vertically, I can plug in that and see where it is, 3 feet horizontally, I can plug it in and see how high it is in the air, right? And at some point, it's going to stop going up, right? And it's going to start turning and going down. So in a parabola, you'll get to some point, and all of a sudden, your numbers will start mirroring your other numbers, right? Away from your axis. That is your position function, all right? That tells you position, where it is located. Instantaneous velocity, all right? That is first derivative of your position function. So if you take your parabola and you take your first derivative, you can tell me not where it is in the air, but how fast it's going, all right? So all of a sudden you can tell me, one, how high is the ball? That's the original function. Now you can tell me how fast is the ball moving when it's been moving for 3 seconds. All right? Now you can tell me the speed, how fast it's going. Velocity is first derivative of position function. And so position is usually written with an S. This usually represents position. Where is it located? Your first derivative is velocity. So you can see it as that, or sometimes you will see it like that. T represents time. How long has it been traveling? So how far is it in the air after 3 seconds? That would be your position function. How fast is it going after 3 seconds? That is your velocity function. The distance a particle moves along a path is defined by this position. That is the distance it moves, where t is given in seconds and the distance is given in centimeters. Find the expression for the instantaneous velocity of the particle. All of those words are asking you to find the derivative. That's what it's doing. Find the expression, that means your new function, that gives me the instantaneous velocity, first derivative of your position function. So all you have to do is you just have to take your position function, which is 18t minus 3t cubed minus 1, and take your first derivative. What's the derivative here? What's my exponent? 1. So 1 times 18 is 18. T to the 0, which means it's just times 1. My t goes away. 3 times 3, my coefficient is 9. T to the second power. And then what happens to that 1 when I take the derivative? It cancels. It's gone. It's 0. Which, by the way, I can then at any point in time tell you what the velocity is of this particle that's moving. After 1 second, my velocity is going to be 9. How do I know that? Well, 18 minus 9 times 1 squared is 9. All right, so that's what it's telling me. It's telling me this is going to tell me in centimeters per second how fast it's moving at a specific point in time. That's what that's going to tell me. All you have to use is first derivative. Try guided practice there. Soccer ball is kicked straight up. All right, so there's something else that our first derivative can tell us. And it's not so much telling us anything differently. It's just how you interpret it. So it's still telling us the slope of the tangent line, all right? But let's say we're riding a roller coaster, all right? I'm riding this roller coaster right here. My slope here is positive. I am going up the hill. Here, my slope is negative. I am coming down the hill. Positive up the hill, negative back down the hill, positive up the hill. See what's happening here? But I have these special points on the graph where I am neither going up a hill or down a hill. I am at the top of the hill. If I were to draw a tangent line at the top of the hill, it would look like this, right? When you are sitting on a roller coaster at the very top of the hill, just before you go over, you should be looking horizontal across. What is the slope of my line at the top of the hill? 0, right? I am neither going up or down. So then what is the slope of my line at the bottom of the hill? 0. Slope of the line at the next hill. So when I find the slope of a line and it's positive, it's going to indicate the graph's going up there. That makes sense. When I find the slope of the line and I find this it's negative, my brain's going to tell me the graph is probably going down there. But when I find the slope of a tangent line and it is 0, it tells me I am turning, right? And these are called extreme values. And this is the extreme value theorem. If f of x is continuous function, so it has to be continuous, meaning I can't jump over something, on a specific interval from a to b, then they have a maximum minimum point either at the end points, that can happen, a maximum at the end because it was an interval, or it's going to happen when your tangent line, slope of the tangent line is 0, when your first derivative equals 0. When your first derivative equals 0, it is called a critical point or a critical value. All right? So let's say I were to take this particular graph and I'm going to say I want to just look at it from A to B. I just want to look at that piece of my function. What this theorem says is the only places that you can have a maximum is either at the beginning, so one of the beginning points, it's going to start here, the ending point, or at a critical number in between. Why is that the case? Well, my critical number is going to indicate a turn, but let's say they had started over here. That's going to be higher than one of my critical numbers. So what you do to figure out what's my highest is you figure out my beginning and ending point, find your derivative, and you set it equal to 0 to figure out where those turns are. Okay? And any of the turns that are inside your interval, those are going to be the critical numbers you test. Then you test your beginning point, any critical numbers in between, and your ending point. You plug them back into your original equation. Your highest y value tells you the highest point you went to, that is your maximum. Your lowest y value tells you the lowest point you went to, that is your minimum on that interval. Okay? So let's look at the example. And the example is hold a roller coaster. All right. And they gave us hideous numbers for our roller coaster. The height of a roller coaster can be defined by this function. Height, that is position function, by the way, on the interval 1 to 12. That is my beginning point and my ending point from 1 to 12. Time in seconds. So after 1 second on the roller coaster and after 12 seconds on the roller coaster. Find the maximum height of the hills from 1 to 12 seconds. So find the maximum point that you are at and the minimum point that you are at in that group. Well, I already know my beginning. I start at 1 second, I end at 12 seconds. Somewhere in between those, I probably turn, okay? So I need to figure out where my turns are. I am gonna take this and I'm gonna take first derivative. So I'm gonna take my position function, all right? And I'm gonna find my first derivative. So 3 times negative 1/3 is just negative 1. My new exponent is 2. 2 times 4 is 8, t to the first power, and the 11/3 zeroes out. This is my first derivative. Anywhere the slope of this guy is 0 will tell me I am turning, okay? It won't tell me anything else except that I'm turning there, okay? So how do I figure out where that's 0? We'll set it equal to 0, right? Does that work? Set it equal to 0. So I'm going to take this function right here, and I'm going to set it equal to 0. How do I find that? Factor out. Negative t minus 8. All right? Set each one equal to 0. T could equal 0 or T could equal 8. All right? So far, so good? Now, for this, I have to look at my interval. My interval is from 1 to 12 seconds. I only test my points in my interval. I am not going to test one of those points. Which one am I not going to test? The 0. Why? He is not in between 1 and 12. Okay? So I can be at my highest point at 1 second. I could potentially be at my highest or lowest point at 8 seconds, because that's a turn in my roller coaster. Or I could be at my highest or lowest point at 12 seconds. I just need to see what those values are. How do I figure out what the values are? Plug them into my position function. My position tells me how high I am. When I plug in a 1, trust me on this because it's a pain, you get decimals, you get about 7.33. You get 11/3 when you plug in a 1. When I plug in an 8, I am going to get 89. When I plug in a 12, I'm going to get 3.67. All right? In feet. So after 1 second, I am 7.33 feet high in the air. After 8 seconds, I am 89 feet high in the air. And after 12 seconds, I am 3.67 feet in the air. What is the maximum feet that I go to? At what point am I at my maximum? 8. That is my max. When am I at my lowest? At 12 seconds. That is my min. And that's what first derivative can also tell you. Slope of the tangent line, but it can also tell you where your turns are. And then you can use those to figure out your max and min for that group that it has given you, or that interval that it has given you.